We have another presentation for this session, and this is by Professor Christian Krabbenhoft. Who is he present? Oh, okay. Professor Krabbenhoft received his Master of Science and PhD from the Technical University of Denmark in 2000 and 2003. He then joined the University of Newcastle before moving to the University of Liverpool, where he is currently the chair of geomechanics. In 2013, he co-founded Optum Computational Engineering to develop user-friendly software for geotechnical engineering practice, and he is currently a consultant for this company. He has held visiting position at a number of universities, including École Polytechnique, ENS of France, DTU of Denmark, Caltech, and Tsinghua University. His research interests include theoretical and computational geomechanics, offshore geotechnics, and constitutive modeling. Professor Krabbenhoft.
Thank you very much. My CV is not quite up to date, I'm afraid. I'm no longer a professor at Liverpool, but I am the technical director of Optum Computational Engineering now. So that's what my job is. Is my presentation here? Or? Oh, okay. Good. So I was given the brief of saying some words about computational limit analysis, and that's what I'll do. And with the outline shown here, I'll have a brief introduction. Then I will say something about what I call the conventional finite element approach, the kind of finite element approach we all know, Plaxis, FLAC, and so on. Then I'll move on to what I will call the Optum approach, which is sort of an alternative to the conventional finite element approach. It's based on optimization, minimum, maximum principles, this kind of thing. I think it has a lot of advantages, and in fact is quite superior to conventional FE. So I'll try to make that case. I'll have a few examples as well, and then hopefully I'll have time to say something about some future developments. So a very basic question in geotechnical engineering is concerned with this problem here. You have a foundation with some loading on it, and the question is, what is the maximum magnitude of loading that the foundation can sustain? And in asking that question, we sort of implicitly understand that if we were to increase the load on top of the foundation, then we would have some settlements, and we would have a load settlement curve that looks sort of more or less like this, at least ideally or schematically speaking. So with the, and what we are interested in is not really the full load displacement curve. We are interested in what we call the ultimate limit load, the maximum load that the foundation can sustain. And with the conventional FE approach, solving that problem involves sort of a more or less fictitious simulation, which is not really necessarily what you want to be doing, but it's what you need to do to solve this question that you're asking, what is the maximum load? So you set up a finite element mesh, and then you start increasing the load, you start stepping up, and at some stage you will have large displacements, and you identify that with failure, and you read off the maximum load. Except that, as I think most people who have done serious finite element analysis know, it's usually not that simple, because usually you get some way up the curve, and then the program has a tendency to start complaining. It might say the soil has failed, or it might say there's convergence problems, or whatever. It may say nothing, and if you continue beyond that point, you might get something that looks like this, and this is what we call numerical problems. Yeah. So, and the question is then, what is the limit load? Is it the minimum load? Is it the maximum? Is it something in between? Do you read off a characteristic settlement, 10% of the footing width, and then read off the load like that? What do? You are sort of, you were supposed to have an answer to a question, and you have now generated 10 more questions. So even though, but even if you get a nice smooth curve like this one, you're still left with the question of how accurate is the solution actually. You know that depends on the density of the mesh, the quality of the mesh in general, what type of finite elements you've used, and so on. You know that if you increase the mesh, you will get something different than if you have a coarser mesh, maybe something like that. So actually you also really have to do a sort of a mesh convergence analysis, have to gradually increase the mesh, do the analysis, which a lot of the time kind of fail or are problematic. And so it's really not very easy to get an answer to this very simple question with conventional FE. So the question is there a better way? And that's of course where Coulomb comes in. And I will not pretend to be a great scholar on the work of Coulomb. He was obviously an outstanding scientist and engineer, and I would think that different people find different things about his many contributions that they emphasize or that they hold particularly dear. To me, it's actually the two words in the title here of his essay, the maximis et minimis. Maximum and minimum principles. As was introduced very nicely by the previous speaker, Coulomb chose to formulate to develop his theory in terms of minimum and maximum principles. And that is something you can do. That is very, very central to the whole optimum approach. And I think it was probably also quite central to the day of Coulomb. There's this very nice quote of Euler that I couldn't hesitate to bring up, that since the fabric of the universe is most perfect and is the work of a most wise creator, nothing whatsoever takes place in the universe in which some relation of maximum or minimum does not appear. So that's a somewhat contentious statement, obviously. You can the thing with the wise creator and all of that, but whether you believe in it or not is one question, but it turns out that if you act as if it's true, if you act as if God exists, so to speak, then life becomes a lot simpler. The laws of nature become a lot simpler. There's some examples here. Just like to emphasize Fermat's principle, which states that light travels so as to minimize the travel time between 2 points. That's all you need to know. Everything else follows from that minimization, in that case, principle. Snell's law of refraction, for example, which is much more complex in a way, much more dirty with angles and so on. Fermat's principle contains actually all the information there is to say about at least some part of light. This is what we call variational principles, and this is sort of the more modern lingo, maximum and minimum principles. And so if we move on to limit analysis or to rigid plasticity, the way it works is as follows. You have, on one hand, the governing equations of rigid plasticity, so that's equilibrium, that's static boundary conditions. You have then also the strain displacement relations. Note that we have only plastic strains, plastic strain rates. There are no elastic strains. We have the yield condition, and we have a flow rule, and we have these well-known complementarity conditions, basically saying we can only have plastic straining if we are on the yield surface. So a fairly, I would say, nasty set of governing equations, but that can be boiled down to something really quite simple, something that actually also the previous speaker already mentioned. There's three ingredients. There's equilibrium and stress boundary conditions, which is also, of course, a kind of equilibrium, the yield conditions, and then the optimization. So what we are saying here is, suppose we have this continuum potato loaded on part of the edge with a load alpha. Alpha is a multiplier times t, a set of tractions. On other parts of the boundary it's supported, and on other parts there's no loading. What is the maximum load that we can sustain here? Well, we can solve these governing equations, or we can solve this optimization problem. We can maximize this load factor subject to equilibrium equations, stress boundary conditions, and yield conditions. Doing one thing or the other, it's the same thing. The lower bound theorem is often misinterpreted as resulting in lower bounds. It actually solving this problem exactly, which is next to impossible unless for very simple problems, implies the full set of governing equations. There's full equivalence between these two different formulations. So that's important to know. And just to emphasize that, a simple analogy, Hooke's law, well, that's F equal to Kx. That's one possible formulation. Or you could formulate it as minimizing 1/2 Kx squared minus Fx, because how do we minimize anything? Well, we differentiate and set equal to 0, and that then produces Hooke's law. So it's the same thing. And in this case, the equivalence is analogous. It's a little more complex than differentiating and setting equal to 0, but it is essentially the same. And there's a well-known apparatus for how to do it. So, but what is the real advantage, in my opinion, is that you don't really have to solve necessarily the optimization problem. Note that it's a continuous optimization problem. Sigma here, the stress field, it's a stress field. It depends on X, Y, Z. But you can come up with useful solutions by constructing what we could call partial solutions. So that's solutions that satisfies the constraints, but that doesn't necessarily imply optimality. So a solution in terms of stress sigma and load multiplier alpha that satisfies all of these constraints but doesn't necessarily solve the optimization problem. Alpha is less than the optimal alpha. Such a solution, since we are maximizing, since we are coming from below, will necessarily then be a lower bound. So the load multiplier will be less than or equal to the true load multiplier. And so a simple example, a weightless footing on a weightless Tresca soil, we could decide to say, well, we have 3 patches here with a constant stress in each of them. So the global equilibrium equations are automatically satisfied since the soil is weightless. And so the only thing we have to really worry about is, so here's the problem. We have to maximize this load Q subject to global equilibrium, which is satisfied automatically, static boundary conditions, and also interface equilibrium conditions. So if we call this sigma 1 and sigma 3, well, then we need to satisfy the Tresca yield condition as well. And so these are the static boundary conditions. So the interface is out here, and this is what I mean by interface equilibrium. So we would come up, we pretty much know that we have to have 0 here because we have a free edge. And then we could try with 2 SU here horizontally, because then this is just satisfied. And that means in the central patch here, we can go up to 4 SU and still have the yield condition satisfied. So in that case, Q is equal to 4 SU. We all know, of course, the exact solution, the famous Prandtl solution, 2 plus pi or 5.14 times SU. But 4 is clearly a lower bound. Another lower bound is, say, 3. Say we had insisted on only SU here horizontally. Well, then we can go to max 2 at most 3 SU vertically. You can solve it in a more systematic way as well, and that's probably what you should do, for at least if it gets slightly more complex. Call these two stresses here P and Q. So P horizontally and Q vertically. And then we have an optimization problem. Again, it's a maximization problem. Maximize Q subject to the yield condition being satisfied out here. So P minus 0 should be less than 2 SU. And in the central patch, Q minus P should be less than or equal to 2 SU. And we can solve this, in this simple case, we can solve the problem graphically. So here are the first 2 constraints, P less than or equal to plus minus 2 SU. and the second set of constraints, they are here. And this area enclosed by the 4 constraints is what we in optimization would call the feasible solution space. Any solution within this space is admissible, is possible. But of course, we would like the highest possible one, which turns out in this case to be 4 times SU. There is the 3 times SU is down here, and there's also kind of an interesting one, negative 4 times SU. So you can actually take the same amount in tension as in compression. So that would suggest you should probably do something about no tension interfaces or something like that. So that's pretty much how it works, computational limit analysis. I don't know, this is sort of a bit dodgy. You would of course like to improve on this 4 times SU solution. The way you can do that is introduce more degrees of freedom, so to speak, into the stress field. So simply have more patches. And in this case, I believe that you get to the exact solution if you insert enough of these wedges like that. But if we look at this situation, if you come from a finite element world, which I kind of do, then you have a tendency to see everything as finite elements. And these are, in many ways, if you put, say, a boundary around them like this, 5 finite elements, 4 triangles and 1 quadrilateral. Or if you wanted all triangles, well, then you could subdivide the central patch there. This is sort of computational finite element limit analysis is pretty much no more complex than this. You can then, of course, discuss, do you want constant stress distributions or do you want linear stress distributions? In practice, you do want linear stress distributions in order to be able to basically account for soil weight, but it's not a big deal to do. The equations, of course, become a little more complex, but at the end of the day, what you do is you take your continuous field, which is your stresses, and replace them by discrete counterparts that typically are interpolated over triangular finite elements. You insert those approximations into the problem, and then you get a discrete problem. These are the discrete equilibrium equations, including incorporating the stress boundary conditions and the yield conditions as well, which are enforced at a certain number of points. And you again have the scalar load multiplier. So this is an optimization problem. The size of it depends on the number of elements. And it is an optimization problem that in many ways traditionally has been the Achilles heel of this optimization approach, because how do you solve it? There was a lot of problems with that for many, many years. People were not motivated very much by mechanics, but this is an important class of optimization problems that are very similar, are very important in a huge number of other applications where there's a lot more money, let's say, than in geomechanics. Finance, scheduling, planning, all these kinds of things. Operations research it's also called. So fortunately, what happened about, I would say probably about 20 years ago or so, was there was a new class of methods came to be known as conic programming methods, developed by applied mathematicians with a focus on exactly these kind of applications in economics and finance, but fortunately designed for problems which are actually, funny enough, very, very similar to the ones that are generated by finite element limit analysis. So we've made good use of those. They are very, very efficient and very importantly also extremely robust. So I usually say that nothing is guaranteed 100% in terms of things working. We are dealing with numerics, but I think I would say it's more likely that you have a power cut than these algorithms fail. Everything can fail, but it's extremely rare. So this offers a completely different robustness compared to to this type of conventional FE, which I see as a huge advantage. Now, and also I should say, I forgot to say that, so this was sort of a lower bound formulation. As I'm sure everyone knows, there is an equivalent upper bound formulation. So there is an approach where you come from above, and I don't think I decided not to go through it here. It's in the paper, my take on the upper bound formulation anyway. It's sort of a slightly more complex than the lower bound one, but it's, at the end of the day, you end up with an optimization problem, which is very similar to this one, except that these matrices, the equilibrium, you could say, is kind of a weak form of equilibrium rather than the strong form. But from a numerical point of view, it's sort of same. And the advantage of this upper-lower bound duality is that the second question of suppose that this is the exact load settlement curve, how accurate is your solution? Well, you have an automatic estimate of how accurate it is because you compute a lower bound, or you can compute a lower bound and an upper bound, and so you know the true solution is somewhere in between. And as you, if you use a coarse mesh, the gap is greater, and as you refine the mesh, the gap between the two solutions shrink. As I've also demonstrated in the paper, this is sort of an empirical result, but even for a very coarse mesh, this one, you can see the average between the upper and lower bounds is very close to the white line here, to what is the exact solution. That's not a coincidence. That is typically how it is. So even if you have two pretty bad solutions, if you average them, you tend to have something of very high quality. But of course, to be completely sure, you have to go to a very fine mesh. So in Optum, we've developed programs for doing these types of calculations for quite a while now. We have two programs, Optum G2, Geotech 2D, and G3 for 3D. Instead of showing you a huge number of applications, I think I would just like to say that arbitrary problems can now be solved to within any desired degree of accuracy. And if you're reasonable about your accuracy, say 1 to 5%, well, then you can do it in a very reasonable amount of time as well. So you can try that out. The few examples I wanted to just go through was also related to Coulomb, earth pressure coefficients. So the earth pressure coefficients for in the case of a purely frictional material and a horizontal backfill, which is sort of the most basic earth pressure problem. There's a huge number of solutions out there in the literature. People have been quite in disagreement about what are the earth pressure coefficients. The codes are also not necessarily in good agreement. So some time ago, we decided to solve this problem once and for all. So use very fine upper and lower bound meshes, and then simply press the button or grind the wheel and have the numbers come out. And so that's what we did. So the active and passive earth pressure coefficients, the diagrams for those. The dots here are the actual finite element limit analysis calculations, and there's also some fits which are very good. They're in the accompanying paper, which I believe will come out very soon. The accuracy here is plus minus 1%, I say, but that's really the worst case scenario accuracy. The actual accuracy is probably something more like 1/10 of that, so plus minus 0.1%. And on the subject of retaining walls, with this approach, when you're in the business of minimizing and maximizing, you might get the idea to minimize or maximize other things than just a load multiplier. And this can be very useful when it comes to design. So engineers do a lot more design than they do analysis, of course. So the design of a retaining wall like this with a single anchor, well, you could say there are three design variables: the wall moment capacity, the anchor capacity, and then the embedment depth. So what you could do is you could say, for a given embedment depth, how do you come up with a design? Well, there's a lot of possibilities. There's an infinite number of possibilities, but there's some extremes where you could come up with a design that minimizes the necessary moment capacity, or the wall moment capacity. That would give you a large anchor force. Then you could minimize the anchor capacity. That would give you a large moment. Or you would come up with some kind of combination where you minimize a combination of the necessary wall moment and anchor capacity. And 3 such solutions are shown here. So this is a solution which minimizes the wall moment. That gives us a very large anchor force. That's what I call P. So 212 moment and 351 anchor capacity. And then the kind of the reverse, where we find the solution with the smallest possible anchor force. That's a lot less. That's half of what we had originally, but the moment is then twice. Or you can come up with some sort of compromise where you have sort of moderate, both moderate anchor force and moment. So this is, and you can take this to a sort of logical conclusion, and quite easily. It requires some calculations, but it's quite possible to basically produce these design charts where these charts are for different embedments. These lines here are for different embedment depths. And the idea is that any solution above this line here it's a feasible design, it's a possible design. So we have the moment and the anchor force, or the prop force here. So these were some of the extremes. So this is the one with the minimum moment, the minimum anchor force, and the compromise one for an embedment depth of 4 meters. And then as you decrease your embedment depth, well, things change. Or as you increase it, things would change as well. So this is really quite useful if you have piles, if you have sheet piles lying around with a certain depth. Well, you can then make your own decision. Do you want strong anchors, or do you want strong walls? There's a huge amount of flexibility in it. So that's also something that I really like about this optimization approach. Now, what people who don't like this approach very much, that's our competitors, to be quite frank, what they say is this is all well and good, but this is only ultimate limit states. And ultimate limit states, yes, it may be important, but it's not that important. What's really important is settlements, and you can't do anything about settlements. That is disinformation. It's completely false. We can handle settlements, and we can actually handle settlements much better as well than conventional FE. What we have to do to handle settlements is have a look at the governing equations, and in particular this one here. We only have, in rigid plasticity, we only have plastic strains. That's what rigid plasticity is, but there is no reason we could also include some elastic strains. I've already included Hooke's law into here, so the total strain rate is equal to the elastic strain rate, and assuming Hooke's law, plus the plastic strain rate. And this modification of the governing equations, the way that manifests itself over here in the optimization formulation, well, you have an additional term in what we call the objective function, the function you actually, in this case, maximize. That's what we call the elastic complementary energy. So you add something to your optimization problem, and then you reproduce the governing equations that you want, in this case of elastoplasticity. And you would then, when you do step-by-step analysis, you have to solve an optimization problem for each load step. So that can be done, and that's included in the Optim programs as well. That's a standard part of the packages. And same with staged excavation and so on. Of course, that can be done as well. That's the same kind of thing. And similar modifications, as I write here, can be made to reproduce the governing equations of pretty much anything: hardening plasticity, coupled pore pressure deformation analysis, dynamics, and a lot more. You can actually do sort of discrete DEM particle type dynamics with this approach as well. So the physics is kind of arbitrary. It's just how you deal with it, really. So Optim is a general finite element program, or it's not just limit analysis, but it is approached from the view of Euler's maximum or minimum postulates. That was also, of course, quite central to Coulomb's work. So yeah, so maybe a better story would be to say, yeah, we can deal with elastoplasticity in an optimization type, minimum maximum type framework, and then if we want rigid plasticity, well, we just turn off the elasticity. We just turn off the elastic strains, and then you have rigid plasticity, which is, of course, a very important problem, and it's useful enough to be able to solve that on its own without having to do the step-by-step analysis. So we are not introducing new physics. It's the same governing equations, but they're approached differently. There's no limitations in terms of the physics that can be dealt with. There are some very significant advantages in terms of computational efficiency and robustness. That's this thing with the upper-lower bound error estimates. And also the ability to provide direct answers to direct questions, as in what is the limit load. That's limit analysis. That's one direct calculation that will give you a number. You don't have to ask the user to sort of imagine a fictitious simulation where he has to first determine initial stresses and then do a step-by-step analysis. That's not what he really was aiming at. He wanted to know one number. Same with design. These types of, say, real engineering questions can be answered in a much more direct way. So just to finish off, a few comments about some future development. So at the moment we have followed the same approach as everybody else. We started developing a 2D program. Once that was out, we said, okay, let's develop a 3D program. And they sort of live their separate lives. Of course, there's something shared between them, but it is two separate programs. One does 2D, the other does 3D. And that is the way it is, I think, for all programs. And so here are the two programs. There's the logos. What you could ask is, what is really the point of 2D analysis at all? The world is 3D, so why do we continue with 2D? And maybe this is one of the not so positive legacies of Coulomb. The Coulomb criterion is a 2D theory in many ways, and we have not really evolved from 2D since the days of Coulomb to a very large extent. That's of course not Coulomb's fault, but we have sort of been quite happy staying in 2D. Because, of course, many of our structures are not bad approximation, can be approximated well as very long structures. Even though there are 3D effects, retaining walls, when they fail, well, it's rarely sort of a 2D failure. Foundations, strip foundations obviously exist, but there's a lot of sort of rectangular, square, circular foundations as well. And slope stability, even, yeah, slopes, they may be very long, but again, the failure tends to be sort of more 3D when it happens. And you run into problems all the time as well, where things are kind of have the feel of 2D, but they are actually 3D. A problem that we have dealt quite a lot with together with one of our clients is these pile reinforced soil slopes, where the question is really how to model these as 2D in a 2D world, because of course what you end up with is this is your real problem, and if you insist on a 2D approximation, what you actually have, of course, is a solid wall. And so this is where it would be nice to sort of maybe do the modeling in 2D and then somehow do the analysis in 3D. Another similar problem, a retaining wall, which you could say, okay, it might, to a good approximation, be a 2D, very long structure, but then you place a foundation here on top, and then you are sort of in trouble. You will spend a lot of time worrying and making approximations that you hope are conservative, but of course not too conservative. And so again, this is mostly 2D, but with sort of a 3D aspect in it as well, a 3D element in it. Yeah, and why 2D? And I'd like to say also that it's kind of interesting to note, many of you probably know this, but all other areas of engineering pretty much have moved into 3D quite a while ago. Mechanical, aerospace, structural engineering, they all have 3D models of their buildings. They might then choose to do the calculations in 3D, or they might choose to look at a facade or a sort of a section of a 3D structure, but it's very, very common to have full 3D models of your structures. It's building information modeling, which is actually now being mandated in most countries. In geotechnics, there's also an increasing tendency to sort of work with digital elevation models, clouds, point clouds. We are regularly sent large data sets, say 10 million XYZ points that define a landscape like this, and then, okay, do an analysis. And what most people really mean by do an analysis is, okay, they might like to do a 3D analysis, but they would also like to do some 2D sections through the 3D analysis. For example, this one here, or something like this. I would like that myself personally, rather than having just one number for the factor of a safety of this sort of 3D landscape. I would like to look at some sections. So again, there's sort of an interplay between 2D and 3D. It's not really one thing or the other. It's sort of both in a way. And that's why we came up with the idea, why not merge 2D and 3D in the same program? So we have G2 and G3 now. If you mix those together, it becomes GX. And so that's what we're working on at the moment, and that's going to come out. So that's going to be a finite element program that has 2D and 3D functionality natively inbuilt, and with really good functionality, really good facilities for, let's say, communicating between 2D and 3D, extruding 2D sections into 3D and taking 2D sections out of 3D models. So that should be interesting to see how that will be received. But for now, I'd like to thank you for your attention. And if you pay close attention, you can see there's an annoying typo there as well. So thank you.
Thank you very much, Dr. Krabben. You gave a very enjoyable and interesting lecture. And if I may make a historical point, I was very pleased to see in your paper that you have quoted a paper of 1973, which is 50 years ago, of which I was co-author with a colleague of mine at Politecnico di Milano, which is on the limit analysis of thin plates by finite elements.
Exactly, yes.
And one of the purposes of that, and that's what the point, was to show that the problem could be solved by using a commercial linear programming method.
Yeah.
So it was good to see that it didn't escape you. That's 50 years ago. Are there any questions, please? Or comments? Yes, please.
Sorry. Thank you. So first of all, thank you. Thank you for your lecture. Very interesting. I have two basic questions. The first one is, how do you deal with boundary conditions? For instance, when you have the whole soil mass, so you have boundary conditions which should be at infinity, but obviously it is not infinity. So
yes.
How do you deal with that one? And I will give you the second one afterwards.
Okay. Yes. We had a lot of discussions about that. There's this concept of extension elements where you can extend the stress field to the infinite. And that is a possibility. It's something that is a complication in terms of modeling, in terms of everything. It's something that complicates things without really providing much gain. So what we say now is the same as the conventional finite element analysis, say, make the domain large enough. And that means, of course, strictly speaking, it is not, say, a lower bound if that's what you're doing. But experience shows that that approach works just fine. I should say as well, with the upper bound method, there's no problems, of course.
No,
you can truncate the domain as you like. With the lower bound method, the numerical lower bound method, we actually also compute displacement-like quantities. So the dual variables to the equilibrium equations, which may be interpreted as some sort of displacement, and it's possible to plot some sort of approximate strain field for a lower bound solution, and then you can get an idea of how large to make your domain. So that's the way we got around it.
Second question is about settlement, calculating settlement, because in that case you should know the loading path. Since you are working in elastoplasticity, you should know the loading path. So what kind of loading path do you impose?
We impose whatever loading path. I mean, that's up to you what loading path to impose. I mean, you impose the loads as boundary conditions, and then your equilibrium equations, your constitutive model, and so on takes care of the rest, as in conventional FE. Yeah. So
it will be monotonous.
Sorry?
Will it be monotonous?
So you're meaning the load path at a point in the soil?
And yes.
Not necessarily. That can be loading, unloading during on the way to global failure.
Okay, thank you.
Yes.
Thank you so much.
Thank you. I think we have a question from Professor Callisto. Yeah.
Thank you. In fact, I have a couple of curiosities. The first one is about the optimization process, because you showed us, for instance, the case of the anchored wall. So I was wondering which quantities are being optimized there, because I think that you have soil strength, but you also have the wall strength, and you also have the anchor strength.
Yes.
So must the optimization variable be a scalar, or can be a set of variables that against which you optimize, or are they linked one to each other? Here, for instance, because you obtain failure, I think that you are scaling down the soil strength, but I think that you are scaling. What is the parameter that you use there?
Okay. Yeah. So the constraints here is equilibrium. So the constraints here are global equilibrium.
Yeah, constraints are in the
yes, and also yield constraints for the wall. And so the moment of the wall should be between plus minus MP, the plastic moment. And it is this MP that is then minimized. So the wall strength is what is minimized.
And in the other cases, it's the anchor strength?
It's the anchor strength that is minimized. Yeah, the anchor is basically, it's modeled as a force. So it's a scalar in that case.
So it's one scalar at a time?
Yes. You could have combinations of scalars. You could do, in the last case, it's sort of a weighted, it's a weighting between the yield moment and the anchor strength.
Okay, yeah.
So say it's
so
50-50.
You establish a relationship between each other.
Yes.
Okay, thank you. And the other thing is that I understand that you should adopt an associate flow rule for plasticity.
Yes.
Because otherwise the theorem will not be valid. Yes. So that puts strong constraints. First on the elastic, perfect plastic constitutive model that you use, but also, at least in my experience, where you have a very deep problem, like pile foundation, and from my experience, you get a very large upper bound solution for piles, for the base resistance.
Yes.
So you get, because associate flow rules for very deep problems means that you involve a very large quantity of soil. So in that case, lower bound and upper bound diverge, are very distant from each other. Can I still average them?
Well, I would think, I mean, this is a, let me just get the relevant equations up. it is clear that there are problems where the confinement, problems that are very, very strongly confined, where the dilation implied by the associated flow rule might give you very large limit loads. In that case, both the upper bounds and the lower bounds would be large. And the question is whether you can trust those values. I think that's a legitimate question. I don't have a hard and fast answer for it. I would like to say, though, that for problems that are strongly constrained, the question is whether you can trust anything, really. Because if you do an elastoplastic analysis and you have 1 degree of dilation versus 0 degree of dilation, you might see a huge difference. So it's some problems that in a certain sense are somewhat ill-posed. So there is that, but in terms of the I didn't show that, I didn't talk about it here. When it comes to limit analysis, the basic upper and lower bound theorems of limit analysis, there's no getting around the associated flow rule. That's something you just have to live with. The way we do elastoplasticity, we can actually do proper non-associated elastoplasticity in an optimization framework. The way it works is that we approximate basically, so the thing is, if you have F up here in the yield condition, you have to have F up down here as well. And usually the F here is the yield condition. But if you take the plastic potential and approximate the yield condition by the plastic potential, then you impose the correct flow rule, but you impose a slightly wrong yield condition. And we have a paper about it from 2012 where we show that if you do what we call fixed point iteration, so you iterate a little bit, then that works out well, and you get the proper non-associated solutions.
Okay. Thank you very much.
Thank you. I think we have time for another question, if any. No. Well, then, thank you very much again. The session is over. And